Hello and welcome to the introduction, H-log P diagram. This is presented to you by Siemens Smart Infrastructure. In this video the structure of the diagram is explained to you. The thermodynamic processes of refrigeration are quite complex. The specific variables for a refrigerant are shown in tabular form in so-called vapor tables. For the following explanations, the specific variables of the commonly used refrigerant, R134A, will be used. To make the connections between these variables more visible, the H-log P diagram was developed. The diagram allows the large number of values from the vapor table to be presented in a simple manner. Nonetheless, without a proper introduction to the diagram, its complexity can be overwhelming. Let's begin. Along the x-axis, the heat content is plotted on a linear scale. This heat content is also referred to as enthalpy, H, and expresses the amount of heat, in kilojoule, that is contained per kilogram of a substance. The vertical straight lines each represent a constant enthalpy. These lines are also called isenthalps. The pressure, P, in bar is plotted on the y-axis. The horizontal straight lines each represent a constant pressure. They are shown on a logarithmic scale to make the most used areas of the chart more visible. These lines are also called isobars. In reference to a typically used H-log P diagram, the lines of the schematic representation will be replaced with lines of a commonly used diagram, after their respective explanation. The latent heat for each pressure, P, the corresponding enthalpy of the boiling liquid, and of the saturated vapor, is transferred from the vapor table to the diagram. The latent heat of evaporation, R, can be measured on the diagram as enthalpy difference between the saturated vapor and the boiling liquid. If you were to add all the enthalpy values of the boiling liquid, and of the saturated vapor, for each pressure on the vapor table, then the results would be curves, which separate the liquid, wet vapor and hot gas zones from each other. These curved lines are referred to as boiling line and saturated vapor line. The point where the two lines meet is called the critical point. At this point there is no longer a difference between the boiling liquid and the saturated vapor. The critical point for the refrigerant, R134A, is at an enthalpy of 391.2 kJ per kilogram, and at a pressure of 40.67 bar. Ratio lines. Wet vapor is a mixture of boiling liquid and saturated vapor. The ratio lines allow us to determine the proportions of gas and liquid in the wet vapor zone. The saturated vapor line separating the wet vapor and hot gas zone can be referred to as 100% hot gas. In the same manner, ratio lines with other constant percentages of hot gas exist within the wet vapor zone. For example, at the ratio line of 30%, the mixture consists of 30% hot gas and 70% boiling refrigerant. The ratio lines are usually drawn in steps of 10%. The axis for the ratio lines, however, will be shown between 0 and 1 with steps of 0.1. The isotherms. Isotherms are lines of constant temperature. Their progression changes abruptly on a change of state, such as from liquid to wet vapor. In the liquid zone, the isotherms are parallel to the isenthalps, because a change of pressure does not affect the enthalpy. In the wet vapor zone, the isotherms run horizontally, parallel to the isobars, for the refrigerant, R134A. In the hot gas zone, the isotherms drop steeply. A small quantity of heat is sufficient to rapidly raise the temperature here. For a clearer diagram, the isotherms are not drawn in the liquid and wet vapor zone, instead their progression is indicated by small angles on the boiling and saturated vapor line. The temperature scale is not only shown along the boiling and saturated vapor line, but also along the x-axis of the hot gas zone. The isentropes. In the wet vapor and hot gas zone, there are lines that provide an indication of the heat losses occurring in technical processes. These lines are called isentropes, and they are labeled with S. For refrigeration processes, the isentropes are most important in the hot gas zone. Path of compression. The isentropes describe the ideal path of compression. In a real process, however, additional losses occur. That means additional effort, in this case heat, is required to achieve this compression. The resulting endpoint of this compression path lies therefore to the right of the ideal endpoint. The specific volume. The specific volume lines show the actual volume of 1 kg mass, at a specific state, and they are labeled with V. The specific volume is highly significant for sizing a refrigeration plant. One should notice that in the vapor table, the specific volume for the boiling liquid is listed in cubic decimeter per kilogram, whereas the specific volume for the saturated vapor is listed in cubic meter per kilogram. You are now familiar with the state progressions of the most important variables of a refrigerant, and the corresponding structure of the H-log-P diagram. This was presented to you by Siemens Smart Infrastructure. Credits for the shown diagrams go to the CoolPak program, from the IPU and Department of Mechanical Engineering, at the Technical University of Denmark. Thank you for your attention.